Welcome to viewers. Here we will discuss zeros of constant polynomial. Earlier we have discussed zeros of polynomial. Zeros of the polynomial means the value of the variable for which the polynomial becomes zero. Now let's define a polynomial of degree n and a polynomial in variable x. Fx is a polynomial of degree n and it is a polynomial in x. We define it as an into x to the power n, an minus 1 x to the power n minus 1, an minus 2 x to the power n minus 2 dot 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 a naught. Now you see the exponents of x are decreasing here. X to the power n, x to the power n minus 1, x to the power n minus 2. Now here we are saying an not equal to 0. Why? If an equal to 0, then this term will not exist. Then this should be a polynomial of degree n minus 1. But we are defining a polynomial of degree n, so an not equal to 0. Now these terms an minus 1, an minus 2, etc. are called coefficients of the polynomial. These are actually real numbers. Now zeros of the polynomial means the value of the variable at which the polynomial becomes 0. So let's fx is a polynomial x square minus 9. Now we see f3 equal to 3 square minus 9, 9 minus 9 equal to 0. That means at x equal to 3, this polynomial becomes 0. Therefore 3 is a factor of 3 is a 0 of the polynomial fx. That means when you are given to find the zeros of a polynomial, you will consider the polynomial an equation with right inside 0. Then solve this equation, you will find the zeros of the polynomial. Now you are given to find the zeros of this polynomial. So let's compare with this equation with right inside 0. It's make it an equation with right inside 0. X square minus 9 equal to 0. This implies that x equal to plus minus 3. That is plus 3 or minus 3. Therefore, zeros of x square minus 9 are plus 3 or minus 3. Right. Now, let's define constant polynomial. What is a constant polynomial? Now, if you see, if an equal to 0, an minus 1 equal to 0, an minus 2 equal to 0, except a naught not equal to 0. In this definition, if a naught not equal to 0, for example, fx equal to, say for example 3, it's a polynomial, constant polynomial, non-zero constant polynomial. Now you see, by virtue of the definition of polynomial, constant polynomial means this will never be 0, right? Because it doesn't contain variable part. So this polynomial will never be 0. So this polynomial does not have any 0. That means constant polynomial has no zeros. No zeros. Right. Constant polynomial fx equal to square root of 2. It is also constant polynomial. Now this polynomial will never be 0 irrespective of any value of x. For any value of x, this polynomial will never be 0. That means this polynomial has no zeros. Fx equal to square root is a constant polynomial. Constant polynomial, that means non-zero constant polynomial. Non-zero constant polynomial. Therefore, this polynomial fx equal to has no zeros. That means constant polynomial has no zeros, because constant polynomial will never be 0. A polynomial will have zeros. We find that for some value of x, the polynomial becomes 0. Now constant polynomial, by definition, this will never be 0. The constant will never be 0. Therefore, it has no zeros. Now think about this polynomial fx equal to 0. It's a 0 polynomial. it's a zero polynomial. Now, irrespective of any value of x, this polynomial will always 0. That means zero polynomial has infinitely many zeros. Means any real number is a zero polynomial. Now we say that there are infinitely many real numbers, right? So zero polynomial has infinitely many zeros. Thus we conclude that a constant polynomial has no zeros and zero polynomial has infinitely many zeros. Means any real number can be a zero of zero polynomial. Now let's discuss one important property of zeros of polynomial and degree of polynomial. Let fx is a polynomial in x and gx is also a polynomial in x. Fx and gx are polynomial in x. These are polynomial in x. Say for example, degree of fx equal to suppose m and degree of gx equal to suppose n and m is greater than n. Then you see degree of fx plus gx. What would happen? This will be m. If fx is a polynomial with degree m, gx is a polynomial with degree n, and m is greater than n, then degree of fx and gx equal to fx plus gx is also m. For example, suppose fx equal to x cube minus 1, gx equal to x square plus 2. Therefore, degree of fx equal to 3, highest exponent is 3, and degree of gx equal to 2, right? Now fx plus gx, try to find it. Fx plus gx equal to x cube minus 1 plus x square plus 2. That means x cube plus x square plus 1. Now what is degree of fx plus gx? What is the degree of this polynomial? 3. Now you see degree of fx is 3, degree of gx is 2, and 3 is greater than 2. Therefore, degree of the sum of the polynomial is degree of the greater polynomial. Means polynomial with greater degree, not greater polynomial, polynomial with greater degree, larger degree, right? Now degree of fx equal to 3, degree of gx equal to 2. Now we find fx multiplied by gx. Find product of fx into gx. X cube minus 1 into x square plus 2. This means x cube into x square plus 2 minus 1 into x square plus 2. Then simplifying this, we find x cube into x square, x to the power 5 plus twice of x cube minus x square minus 2, right? X cube into x square, x to the power 5 x cube into 2 twice of x cube minus x square minus 2. Now what is degree of fx into gx? Degree of the product of this polynomial 5, right? That means this 5 equal to 3 plus 2 means degree of fx plus degree of gx. So what we realize that degree of the product of two polynomial fx and gx equal to sum of their degrees, degree of fx plus degree of gx. This is also one property discussed. Whereas in case of degree of the sum of two polynomials will be degree of the polynomial with larger degree, right? Degree of the sum of two polynomials will be degree of the polynomial with larger degree, greater degree. Here fx equal to x cube minus 1, degree is 3, gx equal to x square plus 1, degree is 2, 3 is greater than 2, therefore sum of the degree of fx and gx is 3, means degree of the polynomial with larger degree. In case of product, we find that degree of the product of two polynomial will be sum of their degrees, right? Next we will discuss factor theorem. Factor theorem. Now remember one thing, 15 is a factor of 120, right? That means if you divide 120 by 15, 15 is a 120, so remainder is 0. So if a number is a factor of another number, when you divide, you will find the remainder 0. But 15 is not a factor of 121. Now you see 121, 15, divide 121 by 15, 15 is a 120, remainder is 1. That means in case of, if it is not a factor, you will find some remainder. Now you remember this theorem, dividend equal to divisor into quotient plus remainder, right? Here dividend means 121 equal to divisor means 15, quotient means 8, remainder means 1. You see, both sides are equal. 15 is 120 plus 1, 121. Dividend equal to divisor into quotient plus remainder. The same logic you can apply with polynomials also. If x minus a is a factor of polynomial px, then you find pa equal to 0. If x minus a is a factor of the polynomial px, then pa equal to 0. This is a factor theorem. Let us explain with the help of example. Say for example, px equal to is a polynomial in x. We write px equal to, suppose, x square minus 5x plus 6. Now you see, you can factorize this with the help of middle term splitting. This is 2 plus 3x plus 6, x square minus 2x minus 3x plus 6, x into x minus 2 minus 3 into x minus 2. That means x minus 2 into x minus 3. Now you see, x minus 2 and x minus 3 are factors of px, right? These two are factors of this polynomial. X minus 2 and x minus 3 are factors of this polynomial px. Now by definition of the factor theorem, it says if x minus a is a factor of px, pa equal to 0. Now x minus 2 is a factor of px, that means p2 equal to 0, p2 equal to 0, okay, and p3 equal to 0, right? Now let's check what is p2. p2 means 2 square minus 5 into 2 plus 6, 2 to the 4, 10 plus 6, 10 minus 10 equal to 0. Similarly, p3 equal to, you put x equal to 3, 3 square, 5 into 3 plus 6, 9 minus 15 plus 6, 15 minus 15 equal to 0. Thus we prove the factor theorem. If x minus a is a factor of px, then pa equal to 0. Now in case of this relationship, we find that if a number is not divisible by another number, you will get a remainder. Similarly, if x minus a is not a factor of, suppose, polynomial fx, then there is a polynomial gx, so that fx equal to x minus a into hx plus gx, right? If x minus a is not a factor of polynomial fx, then there is a polynomial gx, so that fx equal to x minus a into hx plus gx. Here gx is the remainder, hx is the quotient. Hx is a polynomial, it is quotient, and gx is remainder. Now let's discuss this. Say fx equal to x square minus 5x plus 6. Now x plus 1 is not a factor of fx, right? X plus 1 is not a factor of fx. Let's prove this. F1 equal to, f minus 1 equal to minus 1 square, 5 into minus 1 plus 6, 1 minus plus 5 under 5 plus 6, 12, not equal to 0. X plus 1 is not a factor of fx, since this polynomial does not become 0 when we put x equal to minus 1. So x plus 1 is not a factor of this fx. Now you see, if you divide this polynomial by x plus 1, you find some remainder. Let us prove this. So first quotient, you will find x into x square, x into 1 means 1x or x. Now subtract this, you will get minus 6x plus 6. Now you see, you multiply this, this you put minus 6, suppose, minus 6 into x minus 6x, minus 6 into plus 1 minus 6. So you, after subtracting this, you get remainder is 12, right? This is a remainder. Now you see, it's a constant polynomial. So fx equal to, you can write x plus 1 into x minus 6 plus 12. That means fx, x plus 1 is not a factor of this polynomial. We find some remainder. This is remainder theorem says, if x minus 1 is not a factor of fx, then there is a polynomial gx, so that fx equal to x minus a into hx plus gx. That means if x minus 1 is not a factor of the polynomial, you will find another polynomial gx, which is called remainder of the polynomial after dividing fx by x minus a. Now you see x plus 1 is not a factor of this polynomial fx. So when you divide this polynomial by x plus 1, you got some remainder. That remainder is 2. Now applying this theorem, dividend equal to divisor into quotient plus remainder. Divisor is here x plus 1. Dividend equal to here x square minus 5x plus 6. Divisor is x plus 1. Quotient is x minus 6. Remainder is 12. Now this is another polynomial quotient. This is another polynomial. It's a constant polynomial, right? Now let's do some exercise from Cbse curriculum. Say for example, question this: find value of k if x minus 1 is a factor of px in each of the following cases. Now you are given to find the value of k if x minus a is a factor of px in each of the following cases. Now if you are given, suppose first you are given px equal to x square plus x plus k. Now by factor theorem we know that if x minus 1 is a factor of px, then p1 equal to 0. This we discussed earlier. If x minus a is a factor of fx, then fa equal to 0. This is the factor theorem. Now x minus 1 is a factor of this polynomial, so p1 equal to 0. p1 equal to 0. p1 equal to 0 means put x equal to 1 here, 1 square plus 1 plus k equal to 0. That means 2 plus k equal to 0, k equal to minus 2, right? Take another example, say px equal to, suppose k x square root 2x plus 1. Now again x minus 1 is a factor of this polynomial. X minus 1 is a factor of px, therefore p1 equal to 0. Now what is p1? p1 means put x equal to 1 here, k into 1 square, square root of 2 into 1 plus 1 equal to 0. K into 1 square means k, square root of 2 into 1, square root of 2 plus 1 equal to 0. So what is k here? 1 minus 1 plus root 2, or square root of 2 minus 1. This is the answer, k. Right. Okay, we'll discuss similar questions in the next class again. Thank you for watching. Bye bye.